Well, today, November 28th, Monday, we reviewed Newton's second law and its mathematical form like this. Okay, acceleration is proportional to the force, and acceleration is a vector, and it goes in the same direction as the force. And it's scaled down by the mass. In other words, its acceleration is proportional to the force acted upon on the object, and it is inversely proportional to the mass. And last week we have worked on these questions, which is a directly application of Newton's second law. And you have 100 Newton applied to a 5 kilogram object. So the force on the top and mass on the bottom. So you'd have directly calculated that's 20 meters per second square. So that is very simple, and we talk about why this simple. There's no multiplication or constant in front, and it is all because the Newton units is defined as the amount of force that can accelerate a 1 kilogram weight object that at the rate of 1 meter per second. If you do that and with the definition of the force units as newtons, then you have 1 Newton on 1 kilogram and give the exactly 1 meter per second, then you naturally have no constant, no value for this constant, but it still has units. So number 2, we have another question, and resulting acceleration when 300 Newton of force acts on an object with the mass of 300 kilogram kg. And this is simply another example of the above problem. The 300 Newton, and now we have a huge mass divided, therefore the acceleration is very small, 0.1 meters per second. Now, the third question involves a new concept, mass and weight. And what is the weight of 5 kilogram object? Okay, what's the difference between the mass and weight? And we have introduced a new concept of gravitational force. Okay, Newton's contribution to the physics is known for its 3 laws of motion: first law, second law, third law. It means action equal reaction, and his contribution of the gravity. So what Newton says is that there's an attraction between any 2 objects, and they attract each other, and its strength is governed by this formula. And then, well, when he first proposed this, some people will doubt, why don't I see the attraction between the 2 regular objects like a table and a chair, and there is no attraction at all? But then Newton explained that because in this formula, this gravitational constant here is very small. This constant is very universal constant in almost all the back of the book have this gravitational constant. Because this constant is small, you have this regular mass and then distance between the 2 objects, and the regular distance, and you calculate this, the force between these 2 regular objects is very, very small. It's smaller than a fraction of a hair dropping on the table. It's very small. So now, but not if a force, one of the object is huge, like the mass of the Earth. So imagine one of this is huge, and then huge number, the other one is just a regular number. So the attraction between an object on the Earth's surface and the Earth itself, and then that is no longer very small, that could be significant. So even though this is small mass, and then this is the mass, plus these group of numbers are constant. So that constant is shrinking to, we call it g. Okay, and the value of the constant, if you put in the math and put in a g, put in a d square, and that value, if you calculate, is 9.8, which means, so then what is the force, attraction force of to any object by the Earth? The mass times all these, we call it g. So So the gravitational constant is the g. So this g are of that involving the mass of the Earth, radius of the Earth, which is the distance between the object and the center of the mass, and the gravitational constant, which is small. But this number is no longer small because the Earth's mass is big, and even though the gravitational constant is small and Earth's radius is big, but then end up with that value numerically as 9.8 Newton per kilogram. In other words, each kilogram of the object on the Earth's surface will sense the Earth's attraction force of 9.8 newtons. So therefore, the gravitational force is called the weight. Repeat, the force sensed by an object is called the weight, and that weight on the Earth's surface is proportional to the mass. Okay, that's because of Newton's universal law of gravity, and then times a constant, which has the value of 9.8 g. So therefore, mass times g. Okay, and then now let's get back to this question. What are we talking about? Now, number 3, what is the weight? Okay, the gravitational force, and then the gravitational force is simply the gravitational force of the 5 kg times the g. It has a value of 9.8. Therefore, 5.2 times 9.8, do a rough calculation, 2 times 10. So it's about 15 newtons. So 5 kilogram and times this, mass times g is the gravitational force. So that comes from. Okay, you might have noticed why this constant also called g, 9.8. Actually, in fact, it is exactly the same number. Let's see why this g, which is how much gravity force will be sensed by a object, is 9.8 per kilogram. And then and also we know that the acceleration, if you have a free fall object, the object falling at a rate of 9.8 meters per second squared. So these two 9.8, are they the same or coincidence? In fact, it is not a coincidence. It's all related to Newton's second law and the gravitational. Let's look at this. This is the gravity we just talked about, and then mass is whatever mass on Earth, and that will include the Earth's mass and gravitational constant, which is a very small number, and the radius of mass, which is roughly the distance between any object on Earth and to the center of the Earth. So that value is 9.8. But recall that we can write the Newton's second law, so acceleration is the force divided by the mass. And this seems to be a different idea. Well, if you write Newton's second law this way, mass, you multiply the mass this way, your force equal to mass times acceleration. In other words, if you see an object accelerating a certain acceleration and multiply the mass, you will know the force acted upon it. So you put the Newton's second law this way, and you compare these two. So that's a gravitational force and times g, and then the gravitational the force, regular force for any object with that acceleration. You see this g is immediately in the place of the acceleration. So in other words, if you have 1 kilogram object, you see that. So the other argument is that we see that the thing is actually accelerated at this rate. You put this in here, and obviously the force will be 9.8 newtons. So that explains the last question. So last question is not really mathematical, but it's very important. Why you see so many 9.8 there? But see, what is the gravitational force, which is universal force of the Earth as a huge object attracting on anything on the Earth, and which might be small, might be big, but is certainly no compare with the Earth's mass itself. And say the attraction force is you just apply, so m times g. So then 1 kilogram times this acceleration, that's actually the units of that constant, is mass, then that constant shrink into this constant. Mass times g is 9.8 newtons. Therefore, this 9.8 is really the other 9.8 is actually the same number, but even though conceptually they are totally different. This one is the acceleration of the free fall object. This one is the force of this object we will experience. So the statement will say 1 kilogram, okay, and of object that has 1 kilogram in mass will sense 9.8 newtons. And if you say that 1 kilogram object will sense 9.8 newtons, you insert into the Newton's second law 9.8 newtons, 1 kilogram, then obviously you will have 9.8 meter per second squared. So that's why this 9.8 in newtons, this 9.8 meter per second squared is related through the Newton's second law. All right, so that's what we're talking about. Now, one more step. If what is the force of a 2 kilogram object? And then you say mass times 2, so it's 19.8. Therefore, mass times g is 2g is the force, it's 19.6, and divided by 2 kilograms. This is 2 and 2 cancels, you end up with g. So any object, regardless its mass, its acceleration is 9.8 meter per second squared, free fall. If it's free fall, its acceleration is 9.82 meter per second squared. Why? Let's go again. So the force, if say 2 kilograms, 2 times g, so which is 19.86 newtons. And then divide by 2 kilogram, that's the mass. So this 2 and that 2, you get a g. So let's say, okay, if you have 5 kilograms, then you have 5 times g, that many newtons of force. So like we in that program, 5.4, for example, you get something like 50 newtons. Okay, 5.4 newtons, then 5.4 times g, that many newtons, and divided by 2, 5.4 again, 5.4 and 5.4 cancels, and then you get g again. So any mass, okay, any mass, when it falls on the ground, on the Earth, free fall, it will have this acceleration of 9.8. So, but if you take this object to another planet, and then you have the same formula for the gravitational constant, you have the same formula. Where's my formula? Okay, you have the same formula, and here, the g, but the g is different because the mass, this group is called g because the mass is different. For example, on the moon has much smaller mass and smaller radius and gravitational constants, but then this complex is small and g is smaller. Actually, on the Earth is 1/6 of that of the Earth. So therefore, on the Earth, this gravitational force, the weight is much smaller because the g is smaller, but the mass is fundamental quantity, stays the same. This helps. Okay, I will see you next time.